Hey folks, continuing on here in chapter 3. In section 3.7, we are going to learn about a very important, extremely powerful differentiation rule called the chain rule. So in this section, we are going to learn the chain rule. Now folks, here's the deal with the chain rule. The chain rule gives serious power or significant power to all the rules you've previously learned. I cannot stress enough how important mastering this section is. Section 3.7. Mastering the chain rule. It is so important for the rest of your time in calculus, but on an immediate why it's important to master it. The next two sections, really deal with a complete and thorough understanding of the chain rule. For example, the next section, which is section 3.8, it deals with something called implicit differentiation. Implicit differentiation is nothing more than the chain rule, in a different form, but it's the chain rule. Understand the chain rule, you can understand the next section. Then in section 3.9, we study what are called related rates. Without having a thorough understanding of the chain rule, which allows a thorough understanding of implicit differentiation, many would say that related rates will be, basically they're like, word problems from hell. But it's not going to be that bad because related rates, section 3.9, they're just applications of implicit differentiation. Which means, since implicit differentiation is nothing more than the chain rule, it means we're just looking at applications of the chain rule. So again, folks, I can't stress enough how important mastering this section is. Now, the first example I'm going to do is simply a motivational example. It's an example to motivate where the chain rule comes from. So here it is. We're going to consider the function f of u equals u cubed and g of x equals x squared plus 1. Part A, we're going to do an old algebra problem. We're going to do the composition f of g of x. And then in part B, once we've done part A, the f of g of x, we're going to differentiate with respect to x, f of g of x. Then in part C, saying, hey, notice for the functions I've given you, notice that f prime of u, that's 3u squared, and g prime of x is 2x. We are then going to determine f prime of g of x, it's a composition, and we're going to multiply that by g prime of x. So get this written down. This is to motivate where the chain rule comes from. And I'm heading off to the board to work through this. All right, folks, I said this was going to be an example to kind of show us really what's happening with the chain rule. So I gave you the function f of u equals u cubed and g of x equals x squared plus 1. And I said in part A, we were going to do some old algebra. We were going to determine this composition, f of g of x. Well, remember, f of g of x, that's just f of x squared plus 1. And then to find the f of x squared plus 1, you put x squared plus 1 in for u, and you get x squared plus 1 quantity cubed. So our f of g of x is x squared plus 1 quantity cubed. Part B, I said let's dx, let's differentiate with respect to x the f of g of x. Well, so we're going to, in part B, we're going to ddx the f of g of x. Well, here's the f of g of x, so let me put that in place of f of g of x. And the only way we have right now of differentiating this x squared plus 1 quantity cubed is to expand that out, to take x squared plus 1 times x squared plus 1 times x squared plus 1 to multiply it all out, combine like terms, and if we do that, so if we take x squared plus 1 and multiply it by itself 3 times, we'll get x to the 6 plus 3x to the 4th plus 3x squared plus 1. Chopped us. Now we can do term-by-term differentiation. That's not a problem. So we differentiate term by term. We get 6x to the 5th plus a 12x cubed plus a 6x. And you know what? I'm going to clean this up just a little bit. I mean, I'm going to factor. I can factor out a 6x. And that leaves me with an x to the 4th plus a 2x squared plus 1. And this x to the 4th plus 2x squared plus 1, that actually factors. That factors to x squared plus 1 times x squared plus 1. Or as simplified as possible, it's 6x times the quantity x squared plus 1 quantity squared. So, let's see where we're at. We have differentiated with respect to x the composition of those two functions, and this is what we have as the derivative. On part C, I'm saying, hey, let's do f prime of g of x and multiply that by g prime of x. Now, I think I told you on the slide. If not, we can quickly compute it here. F prime of u is 3u squared, and g prime of x is 2x. So we need to find the f prime of g of x. Well, that's the f prime of, well, g of x, which is x squared plus 1. And then the f prime of x squared plus 1, well, we take x squared plus 1 and we put it in here to f prime. We put it in for the u, and that gives us a 3 times x squared plus 1 quantity squared times, well, g prime of x we know is 2x. So if we clean this up, we get 6x times x squared plus 1 quantity squared, which is the exact same thing as what we had in part B. Now, I wouldn't be taking this time if it were just some crazy coincidence. So let's string together what we did here. I mean, we have the same answers. So now how did we get the 6x in part B? How did we get the 6x times x squared plus 1 quantity squared? Well, we got this answer here by ddxing fg of x. In part C, how did we get the 6x times x squared plus 1 quantity squared? Well, we got it here by computing f prime g of x times g prime of x. So since these are equal, it seems reasonable to say what produced each of them should also be equal. In other words, the derivative with respect to x of f of g of x is equal to the f prime of g of x times g prime of x. And that, folks, that is exactly what the chain rule is. So let's head back to the slides. I'm going to write the chain rule down in the theorem. So here we go. Hey folks, that example that we just looked at, that motivational example of where the chain rule comes from, we've just seen in that example that when you differentiate with respect to x a composition of functions, so when you ddx f of g of x, that's equal to f prime of g of x times g prime of x. That is exactly what the chain rule is. It deals with differentiating composite functions. So let me write down the chain rule. I'm going to write it down in two versions. So I start off by saying, y equals f of g of x. It's a composition of functions, and it's differentiable, and it's given by, part one, I'm saying dy dx equals dy du times du dx. Just wanted to use the Leibniz notation. Or the second version, dy dx equals, differentiating with respect to x, f of g of x, and that equals f prime of g of x times g prime of x. Now, before I go further, you're going to hear me talk about this a little bit more, but notice when you have f of g of x, okay, and we're saying when you ddx f of g of x, it equals f prime of g of x. Well, f prime, that's kind of like we're saying that's the derivative of the outside function. And then times g prime of x, well, that's saying the g prime of x, that's the derivative of the inside function. So you're going to hear me talk more about this inside function, outside function, and it'll make sense when we do an example. But I do want to mention it one more time. I always found the key to using the chain rule is identifying the inside function and the outside function. And our first example is going to illustrate this. So in this example, we're going to differentiate the function y equals quantity x to the fourth minus 3 to the fifth power. So get this example written down. It's our first example of using the chain rule. And I'm going to head off to the board and work through it. All right, folks, we've seen the chain rule. It's a really powerful rule. It gives all of our other rules a lot more power. And you heard me start to talk about, there's an inside function, there's an outside function. That's what composition of functions are all about. The chain rule allows us to get the derivative without having to go off and determine, hey, what two functions are being composed to give us a function? We can visually see it. We can determine the outside function and the inside function. And let's look at what I'm talking about in this example. Differentiate y equals the quantity x to the fourth minus 3 to the fifth power. First off, without the chain rule, you would have to take x to the fourth minus 3 and multiply it by itself 5 times. That's why the chain rule gives all of our other rules a lot more power. So here's how we get the derivative. I'll denote the derivative here as a y prime. The outside function here is the fifth power. The inside function is x to the fourth minus 3. So the chain rule says do the derivative of the outside. So the derivative of the outside, 5 comes out front, and subtract 1 from the exponent. So that's the f prime part of when you look at the chain rule. We've done the derivative of the outside. Now you multiply that by the derivative of the inside function. Well, x to the fourth minus 3 is the inside function. Derivative of x to the fourth minus 3 is 4x cubed. That's it. So let's head back to the slides and see what more I have to say before we do a lot more examples. All right, hopefully you saw in that example, it's not too bad to identify the outside function. Obviously, it's pretty friendly to see what the inside function is. And so doing the chain rule wasn't that bad. I always debate on showing this or not, and I thought, oh, what the heck, I'll go ahead and include this. The chain rule, we can use the chain rule to write what's called a generalized power rule. So here's the generalized power rule. Use a differentiable function of x, n is a rational number. Then when you ddx u of x to the n power, that derivative is n times u of x to the n minus 1 times u prime of x. Or I could write it as n times u of x to the n minus 1 times du dx. Instead of using the u prime of x notation, I could use the Leibniz notation, du dx. All right, time to do an example. This example, make sure you write down all the parts. I'm going to do, well, it has 7 parts here. So we're going to practice doing 7 different derivatives. And of these 7, I believe about 3 of them, I'm going to ask you to try. So here they are. So there's A, B, and C. Get those written down. There's D, E, and F. Get those written down. And there's part G. So like I said, there are 7 parts. So if you have to pause the video right now to write down all the parts, do that because these are 7 examples of using the chain rule. So now I'm going to head off to the chalkboard and work through this example. All right, folks, this example had, 7 parts to it. I can't get all 7 parts up onto the chalkboard at once, so let's focus on these 3, then I'll erase, etc. So in part A, differentiate y equals 3x squared plus 1, the quantity 3x squared plus 1 to the 4th power. So the chain rule says, do the derivative of the outside. The outside function is the 4. So that is a 4 times 3x squared plus 1 quantity cubed. Now multiply that by the derivative of the inside function. Derivative of 3x squared plus 1 is 6x. That's it. Part B, the function square root x squared minus 2x plus 7. First thing I would do is rewrite that as x squared minus 2x plus 7 quantity to the 1/2 power. So why don't you do that, and then why don't you pause the video and finish off do part B. Once you've done it, restart the video. I'll be here at the board to make sure you did it correctly. Alright, I said the first thing to do, rewrite the function as x squared minus 2x plus 7 to the 1/2 power. So here we go, using the chain rule. The derivative of the outside, so that gives me a 1/2 x squared minus 2x plus 7 to the negative 1/2 times, okay, now the derivative of the inside function. So the derivative of the inside function is 2x minus 2. That's a great derivative. Now if you wanted to simplify it, I suppose you could rewrite this piece here with a positive exponent, so drop it to the denominator, and then you'd have a 1/2 times the 2x minus 2. Well, if you factor a 2 out of here, the 1/2 times the 2 would be 1. So this would simplify like that. Or if you wanted to get it back into a radical, I hope you got that for part B. Part C, so check out part C. You still have to remember old rules. We have a product of 2 functions, so we have to crank this through the product rule. So here we go, product rule. I'll call the derivative here dy dx equals, okay, the derivative of the first function, 2x times the second plus the first function times, okay, now when doing the derivative of the second function, we have the chain rule taking place. That's a 4 times a 3x minus 5 to the 3rd power times the derivative of the inside, which is 3. Just couldn't quite get it on the same line, but that's a times 3. And you know what? Look, that's the derivative. Let's just practice a little bit of simplifying. So that's a 2x times a 3x minus 5 to the 4th power plus 3 times 4, so that's a 12x squared times 3x minus 5 cubed Now I could factor out a greatest common factor. Look at each term. Each term has 2x as a common factor. And each term has a 3x minus 5 to the third power as a common factor. So if I factor this out of the first term, I'm just left with a 3x minus 5 to the first power. So I could just write that as 3x minus 5. If I factor this out of this term, I'm just left with, a 6x? And I could eventually write it. I could combine like terms. Alright, so, okay, now I have to erase the board. So let me erase the board and get parts D. I'm going to try to get parts D, E, and F up here. So bear with me as I erase. Let's see, here's part D. Y equals 3x squared over 2x squared plus 1. And all of this is raised to the fourth power. I want you to try part D. I want you to try to get this one on your own. So I want you to pause the video, do part D. Once you're done with part D, restart the video, and I'll be here at the board and we'll work through it, and hopefully you have a correct answer. Alright, let's see how you did on part D. So, you know what I'll call the derivative of y prime. So we start off and we have a 4 times a 3x squared over 2x squared plus 1 to the third power. So that's the derivative of the outside. Times, now when we do the derivative of the inside function, we do the derivative of 3x squared over 2x squared plus 1. We have to use the quotient rule. So here we go. Derivative of the numerator, 6x, times the denominator, minus the numerator, times the derivative of the denominator, all over the denominator squared. And you know what? I'm not going to simplify that anymore. All right, part F. It's the constant multiple rule here, or part E. So the derivative is 5. All right, now here, the inside function is the 3x. So you just think, okay, I'm trying to get the derivative of sine 3x. So what's the derivative of sine? Derivative of sine is cosine. So we'd have cosine 3x times, now the chain rule says you have to do the derivative of the inside function. Well, the derivative of the inside function, the derivative of 3x, is 3. And you know, I would probably write this as a 15 cosine 3x. Now for F, I would personally make my first step rewriting sine squared 3x as sine 3x quantity squared. And here we're going to have a nested chain rule, where there's a chain within a chain. So, you know what? I'd like you to pause the video, see if you can get part F. Take your time with it, but see if you can come up with the correct derivative. When you're done, do it. When you're done, restart the video. I'll be here at the board working through it. Hopefully you got it correct. Okay, here we go. Let's see how you did on part F. Here I'll call the derivative dy dx. So I start off, all right, the outside function's a 2, so the 2 comes out front. 4 times 2 is 8. Then we'll have sine of 3x, and that would be raised to the first power, times, okay, now I have to do the derivative of the inside function. Well, notice the inside function has an inside function. there's a 3x. So I have to take it a step at a time. So the derivative of sine 3x, well, the derivative of sine is cosine. So I'd have cosine 3x times the derivative of 3x, which is 3. I did f right after e so we could see what was happening. F's a little more challenging in the sense that there's a chain within the chain. So, and you know what? I would write this one as 24 sine 3x cosine 3x. So, if you got part F, good for you. That was a challenging one. So we had one more part to this example, part G. So let me do a little erasing here, give some room so we can look at part G. So part G was y equals the sine of cosine x squared. All right, I'll call the derivative y prime here. All right, so, boy, my inside function is cosine x squared, and it looks like there's an inside to that, which is x squared. So I take it a step at a time. First off, we have the sine of this mess. So we start off with our outside, sine. What's the derivative of sine? Derivative of sine is cosine. So we have cosine of cosine x squared. So that's like the derivative of the outside function. Okay, now times, we have to do the derivative of the inside function, cosine x squared. So what's the derivative of cosine? That's right, it's negative sine. And then there's another inside that we have to differentiate, the x squared. What's the derivative of x squared? That's right, it's a 2x. So, I mean, if you wanted to, I suppose you could write this mess as a negative 2x, sine of x squared, cosine of cosine x squared. That's a little bit more challenging of an example. All right, folks, we've looked at a total of 8 examples practicing using the chain rule. It is extremely important that you get this under control. The next 2 sections are relying on the fact that you have a good grasp of the chain rule. The best way to get a good grasp of the chain rule, do the homework, do the exercises. So at this time, head off, do the section 3-7 exercises. Get this under control. Thanks for watching.